We're in the tutorial mode for SPSS Now, a single sample t-test. Here are our learning objectives: interpreting and writing up results APA style, increased familiarity and confidence with SPSS, analyzing data with a single sample t-test, and hypothesis testing with the single sample t-test. First, we'll look at the completed APA style report. We'll see as an example and learn how to interpret it. So here's our write-up that we'll be working with. It reads, based on an interview of 89 statistics students, the belief that college students typically have one sibling was rejected, comma, italicized T, open parentheses, 88, close parentheses, is equal to 6.62, comma, P less than 0.05, period. The results support college students having a greater number of siblings, open parentheses, italicized M, equal to 2.20, comma, italicized lowercase s, equal to 1.71, close parentheses, comma, 95% uppercase C, uppercase I for CI, open square bracket, 1.84, comma, 2.56, close bracket, period. All right, so what does that tell us? It's saying that based on a review of 89 statistics students, that's our sample. That's the people that we interviewed. The belief that college students, so that's our population, college students, typically have one sibling. So that's our null hypothesis, that college students have one sibling, that they're typically from families where there's two kids, was rejected. And that this was a t-test. It had 88 degrees of freedom. It was equal to 6.62. And if we were to believe the null hypothesis, this could happen, but with probability less than our alpha level of 0.05. So the results support college students having a greater number of siblings. And then we're given the descriptive statistics for our sample, and we're also given a 95% confidence interval where we are likely to find the true population for number of siblings. That's somewhere between 1.84 and 2.56 siblings on average. So when we're breaking up this APA style write-up, again, you want to be able to find the important piece of information, so sample size. In this case, it's 89. Our population, it's the college students. That's who we're going to be generalizing our results to. And we need to have an idea of what was the null hypothesis. In this case, typically, that students would have one sibling. And then we want to know, well, what was the sample mean equal to? And we can find that as an uppercase M. It's 2.2 siblings. Now, if we were to hand calculate the single sample t-test, we would need to be able to figure out what is our standard error. And as you know, the formula for a standard error is the standard deviation divided by the square root of the sample size. And that information is provided in this write-up. 89 is the size of our sample, and the estimated standard deviation is 1.71. So our standard error is calculated as the standard deviation of 1.71 divided by the square root of our sample size, which is 89. And so we get a standard error of 0.181. And that's really important because that is our unit of measurement. Just like if you want to know like how tall someone is, we use a foot, kind of an arbitrary measure, but it's important to us. So we use the foot to say, well, how many feet tall is this person, right? And other systems could have a different unit of measurement. And we need to calculate the standard to kind of get an idea how different is our sample mean of 2.20 from where the null hypothesis said we could expect to get a sample mean of 1.0. The distance between the null specified mean of 1.0 and the sample mean of 2.20 is measured in units of standard error. So the t-test tells us how many standard errors are there between the null specified population mean and the sample mean. In this case, it's quite a lot. Anytime you're getting more than 2 standard errors, that's something to get your attention. And if you're 3 standard errors, even more so, right? So anytime you're beyond 2, you start to say, there's something perhaps that's going on here. And we're told in our statistics that the probability of getting a sample mean this extreme if we were to believe the null hypothesis, well, it'd be a very low probability event, p less than 0.05. It'd be unexpected, surprising, not consistent, and would lead us to reject the null. And so, because the probability was less than or equal to 0.05, the null hypothesis was rejected as something of value to help us to make predictions, right? Because the null hypothesis is like, hey, you can expect it to be around 1. And it wasn't. It was 2.20. And that null hypothesis is, we're basically saying it's misleading, because that 2.20 would be like this really extreme result if we were to believe that null hypothesis. So we cross off the null hypothesis and we reject it. Now we can also provide the reader with a 95% confidence interval. And the 95% confidence interval says, you know what? There's a 95% chance that this interval of 1.84 to 2.56 contains the population mean. So that gives the reader an idea of where is it likely to actually be. Now, the example we just walked through is where we reject the null. Let's take a look at an example where we would retain the null. So here, let's say the sample mean was 1.3, right? The null hypothesis says, typically college students have one sibling, and well, our sample, it was 1.3, which is different than 1. But again, the question is that difference such a low probability, such an unusual event, that we should reject the null? And in actuality, it isn't. The difference between 1 and 1.3 is reasonable. It's expected, not surprising. It's consistent with the null hypothesis. We would retain the null hypothesis. We'd say it did a good enough job. And our p-value would be bigger than 0.05, saying, hey, this is a probable event. You can be comfortable that the null hypothesis is doing the job that it should. So the null hypothesis would be retained. Now, what if your sample mean, what if your sample is skewed? Because the sample that we're working with in this example, it is positively skewed. And as a result, you might be wondering, well, should I use the single sample t-test with it? And that's always going to be a really good question to ask your instructor or your employer or the people that you're working with. What's the kind of the culture there? But let me give you some idea why there are a group of people who would feel comfortable with using the single sample t-test even if the sample is skewed. If we take a look at the central limit theory, it says that as you increase the sample size, it doesn't really matter the characteristics of the population. Population can be positively skewed, negatively skewed, bimodal, uniform. It doesn't really matter as the sample size increases. In this case, our sample size was 89. So from a population, for example, that would be very positively skewed, and even if our sample, as a result, is positively skewed. If you were to look at a distribution of those sample means, so here's an example where we have 26,000 sample means, samples of size 89, where all the sample means came from a positively skewed population. The distribution of sample means looks really normal. It's not perfectly normal, right? You can see it's just slightly off here and there, but it's really close. And so, in general, many people go with the idea that if the sample size is 30 or greater, then it's probably going to be okay. But again, always check with your instructor or employer, best way to proceed there. Okay, so APA style really values writing something up in a way that's understandable and succinct. So the way that I walked you through the APA write-up, it wasn't as succinct as it could be. And that was okay, because I wanted to help you better understand things like the null hypothesis and the confidence interval. But let's say I was just going for it to be succinct, and I didn't need to include confidence interval. Then if I had a normal distribution, I might say, based on an interview of 89 statistics students, comma, college students typically have more than one sibling, open parentheses, italicize m equal 2.20, comma, lowercase italicized s equal to 1.71, close parentheses, comma, t, open parentheses, 88, close parentheses, equals 6.62, comma, italicized p less than 0.05. Now, in this write-up, the null hypothesis isn't stated clearly. And generally, it isn't. I was making it clear because sometimes it can be hard to wrap your head around the null hypothesis and hypothesis testing in general, right? But typically, when you see something written up, it just lets you know, like, this is our conclusion. And so this is a lot shorter because it didn't state the null hypothesis, it just stated the conclusion. If the distribution is skewed, you would have a very similar write-up, except that you would also include the median. So someone could see the impact of the distribution having been skewed on that difference between the mean and the median. You would also provide the interquartile range and a measure of skewness. And always check with people you're working with on that. Okay, so that kind of gives you an idea of what does the write-up look like, what does it mean, because now we're going to do the exploration where we get the information to include in such a write-up. So we're looking at the SPSS variable view. We have two variables, a sibling variable and a high school GPA variable, and we're just going to be focusing on the sibling variable in this case. And our first step, after we've kind of taken a perusal, looked through the data, is to switch over to the variable view and make sure that that's set up appropriately. For a single sample t-test, we want our dependent variable, we need it to be a scale variable. So we head on over and make sure that, yes, our variables are scale, so we're good there. All right, so now let's go ahead and get our descriptive statistics. The descriptive statistics are what we use to describe our sample. So with SPSS, we go to the Analyze drop-down menu, click on Descriptive Statistics, and there's lots of different ways to go about this, but for this tutorial, I'm going to go with Explore. I'm going to move number of siblings on over to the dependent list. And we'll go ahead and add the histogram. So to do that, I'm going to click on Plots, and click on Histogram, and click Continue, and then OK. Okay, so SPSS is ready to generate our descriptive statistics and give us the histogram. We need to take a look at this to evaluate the normality of the variable, because ideally our variable should be fairly normal, and then everyone is very happy with us using the single sample t-test. But if our variable is skewed, then we owe it to our reader to make sure we communicate that. So we have to look ourselves so we can communicate it accurately. So here's the descriptive statistics presentation by SPSS, and it gives us our mean, it gives us our median, likewise the standard deviation, the interquartile range, and skewness. And so I point those out because if the variable is normally distributed, we'll share the mean and standard deviation. If it's skewed, then you want to make sure you include the median and the IQR, and we'll look at the skewness to see how skewed is this variable. So here are the three tests of normality that we do. First test, we compare the mean and the median. And if they are so far apart that the mean would just be misleading to report, then we're going to say this isn't a good indicator that it's normally distributed, and we really should provide both the mean and the median, right? In this case, 2.20 or 2, subjectively, I'm going with it's close enough. Okay, the second of our three tests would be to look at our measure of skewness and compare it to twice the standard error of skewness. And what would be consistent with the distribution being fairly normal is if that absolute value of skewness was less than 2 times the standard error of skewness. But it isn't. The absolute value of skewness is 1.286, and that's larger than 2 times 0.255. That is, 1.26 is greater than 0.510. So of our three tests, this passes the mean and the median being fairly close, but it does not pass looking at the measure of skewness. Finally, we'll take a look at the histogram to likewise get a sense. Does it look fairly normal, or is it just like really shouting out at us that it is skewed? And this histogram is clearly indicating it's skewed. Part of it is blocked by this note here. So we have a clearly skewed distribution. Now, why these three tests? Well, if the mean and median are really different, then again, it's going to be important to share the median. The skewness can give you a good idea if the distribution is skewed, but as the sample size increases, then even a really small amount of skewness would suddenly get flagged as the distribution is skewed, but that skewness might be so minute as not to be very meaningful. So we check into it, but we're not basing everything on it. And then with the graph, likewise, we're going to look at it, and for small sample sizes, it can look really messy, but as the sample sizes increase, if it looks really heavily skewed, and that's a good indicator, again, that we're working with the skewed distribution. So those are our three tests. So we're going to go with this being a skewed distribution. So we would say, again, based on an interview of 89 statistics students, college students typically have more than one sibling. We're providing the mean, the median, the IQR, the skewness, and then the statistics there. All right, so now that we've done the descriptive statistics and we know that this is a skewed distribution, and we've decided that, at least for this tutorial, that it's okay to proceed, then next step is to go ahead and calculate the single sample t-test. So go to the Analyze drop-down menu, click on Compare Means, choose one sample t-test, and we'll move the number of siblings over to the test variables. And we're going to set our test value to 1 because the null hypothesis is that college students have one sibling, right? And this, by the way, is going to be a two-tail test, because if college students had a lot less than, on average, than 1, or if they, on average, had a lot more than 1, we're going to reject the null hypothesis. So it's a two-tail hypothesis test. So put in the 1, click OK, and here's the SPSS output, and it starts off by just giving us some descriptive statistics. The sample size is 89, the mean is 2.20, standard deviation is 1.713, and the standard error of the mean is 0.182. These statistics were also available on the Explore stats. But if we had skipped the Explore stats, we wouldn't have been able to assess the normality, because it isn't giving us things like the median or the skewness, nor a histogram. And then further below, SPSS gives us our one sample test inferential statistics. This is where we decide, should I reject the null hypothesis or not, based upon my sample. So the distance, as mentioned earlier, between the null hypothesis, specified null of one sibling, as a typical number of siblings for college students, compared to the sample mean of 2.20, that is 6.62 standard errors between them. And as mentioned, anytime you get like more than 2 standard errors, you're like, something could be going on. And if you get to 3 and more, just the idea that something could be going on, this is not normal, increases more and more. So 6.62, that's a really big red flag there, that this is likely to be a very low probability event. Okay, our significance two-tail. So SPSS is giving this to us for a two-tail hypothesis test, and it's saying the probability is less than 0.001 or less than 1 in 1,000. If we were doing this as a one-tail test, then we would take the significance two-tail and we would divide it in half. And then compare it to our alpha level of 0.05. So just that as an aside to be aware of. Okay, so we're rejecting null hypothesis because two-tail test, significance two-tail is less than 0.001, it's below our alpha level. So given that a true null hypothesis, where it had a mean of 1, would be unlikely to produce this result, a sample mean of 2.20, or p less than our alpha level, we will reject the null hypothesis. That is, this is a surprising event, and the low p-value says it's surprising. Reject that null hypothesis. And then we would write it up. So we would say t, and in parentheses 88. So the t is because it's a t-test. The 88 is our degrees of freedom, and I'll just point out the degrees of freedom is your sample size minus 1. So if your sample size is 89, degrees of freedom is 88, and that's put in parentheses. Also a handy way to always know what the sample size is just by looking at degrees of freedom. You go in reverse, you just add 1. So t, open parentheses, 88, close parentheses, is equal to 6.62, telling us that there are 6.62 standard errors between the population mean as specified by the null hypothesis and the sample mean. And that comma, and that this is a really low probability event. P is less than or equal to 0.05. So null is rejected. And then we can also provide that confidence interval. So SPSS will give us, in the output, it'll say, hey, your test value, in this case was 1. And then it'll say 95% confidence interval of the difference. And it has lower and upper. So the lower is 0.84 and the upper is 1.56. And here's the thing to keep in mind. To find out, well, what is the lower boundary, you need to add the test value plus whatever SPSS puts in this lower box. So in our case, we're adding 1 plus 0.84 for the lower boundary to get 1.84. And we're going ahead and adding 1 plus 1.56 to get 2.56 for our upper boundary for our 95% confidence interval. So if we were to do this over and over again with different samples, 95% of the time, the population mean would be found in this confidence interval. Okay, so that's our tutorial. So what you would do at this point as a student in my class is you click on the game option and go ahead and do the challenge of completing this with fewer hints, just 3 hints total. And I wish you the very best luck.